So, good evening, guys. So, today we are going to discuss about the chapter like work, power, and energy. Okay. In this work, power, and energy, okay, for example, we are having different topics in this. Like, for example, the first one you will be having regarding the work concept, okay, which we are going to discuss today. Okay. Then, second, we are going to have regarding the energy. Okay. Then third, we will be discussing about power. And in this energy, we are having another part which we need to discuss, that is law of conservation of energy. Then regarding the equilibrium of the particle, that is, there will be three types of equilibrium: stable equilibrium, unstable, and neutral equilibrium. Regarding that, we will discuss. And after that, we will be discussing about collisions. Okay. So today we will be discussing about the topic of work. Okay. Right. So regarding work, we will be discussing. Okay. So it is about the work concept today. Okay. Right. So first we will discuss like what is meant by work actually. What is meant by work? Okay. Many people will say like actually doing something, right? Okay. So basically we'll be having two types of work. Okay. One is the mental work and other one is the physical work. Like for example, right now you people are listening to this particular class. Okay. That is a kind of mental work. Okay. You are listening to music. That is also mental work. Okay. You are studying. That is also, it is involving some kind of mental work there. Okay. But we are not going to discuss about all those. We are going to discuss about only physical work in our concepts right now. Okay. So what is meant by physical work means, like for example, just a minute. So what is meant by physical work? Okay, look at this. So when do we say that actually we are doing some physical work? Okay, look at this. So for example, you are applying some force on any body. Okay, if you are applying some force on any body, and if that particular force displaces that body, okay, if that force, okay, why did I use this word component of force? That I'll let you know. Okay, if this force displaces a body in its direction, then we say that work is done by that force. Okay, so for at any point, if work needs to be done, okay, first some force should be active. Okay, that force, if it is displacing that body, and that too in its direction of motion, okay, in its direction, then we say that work is done. For example, if you are applying force on a wall, okay, there you are applying force on a wall, okay, I mean WALL, okay, we are applying force on a wall. So if that wall, you are applying the force, but if the wall is not displacing, then we don't say that work is done because there is no displacement there. Okay, so whenever there is some force is acting and the body is displacing, then we say that work is done. Okay, let us see a few examples in which cases work is being done so that you can understand it better. Okay, look at that. See that a porter is actually pushing something. Okay, he is applying force and he is pushing. So this is an example. Next, look at that. A person is actually pulling a rock. Okay, with the help of some tensional force in this particular rope, with the help of some tensional force, he is able to pull that particular stone. Okay, next, okay, see, just look at this. A person is jumping from the top floor of a building towards the ground. Okay, here also work is done by the gravity is doing some work here because it is pulling that person in the downward direction. Because of the gravitational force, This person is moving downwards. Is it okay? So there is a force and the body is displacing in that direction. Okay. Next. Yeah, look at this. So here, if you observe, a person is pulling this trolley in which a girl is sitting. Okay. So he is actually pulling that at certain angle to the horizontal. Look at this, at what angle? It is at an angle of 30 degree to the horizontal. Okay. So when the angle is 30, now this total force is not actually pulling it. Okay. This force, we can resolve it into two components. That means we can divide that force into two components. One is this horizontal force and another one is vertical force. Okay. That is the reason sometimes, every time, only force need not pull the body. Even a component of force also can pull the body. Okay. So here, that 50 Newton, which is acting at an angle 30 degree, okay, its horizontal component will be responsible to pull this particular trolley in this direction. Is it okay? So that's why when a force or a component of force displaces a body in its direction, then we say that the work is done by that particular force. Is it okay? So these are the examples. So you can take it down. Okay. Next, let us go to the next slide. Okay. So what is the, okay, we understood what is meant by work done. Okay. But how to calculate that work? Okay. So work is equal to, what is the formula, my dear? Basically, force and displacement, both are vector quantities. That means they'll be having the direction. Okay. So work done is given by F vector dot S vector. That means it's a multiplication of force and displacement. Okay. As the both are vectors, we have to do some products which is applicable for vectors. Okay. In that, why did I use this dot product? I'll let you know. Okay. So work done is equal to F vector dot S vector. Okay. It is equal to, in dot product, if you remember, A vector dot B vector is equal to how much it is? AB cos theta. Okay. Same thing, we are applying it for Fs cos theta. Okay. F vector dot S vector means it will be equal to Fs cos theta. Similarly, it is, we can also write it as F cos theta into S. Why did I use this F cos theta here? It is look at this. Here, if you observe, this 50 is acting here, no? But the displacement is actually horizontal. What is meant by theta in the previous formula is, okay, the theta is angle between force and displacement. Theta is angle between force and displacement. That angle will be there, no? That one we are calling it as theta. So what is the formula for work done? It is Fs cos theta. Okay, remember this formula. I'm going to use this later once again. Okay. Now, why did I use this dot product here? It is because work is a scalar quantity. That means it has only magnitude. It doesn't have any kind of direction. Okay. It has only magnitude, but it doesn't have any kind of direction. Next. So what is SI unit of this? It is a joule. Okay. So it can also be represented as capital J. And the CGS unit of work done is, it is erg. Okay. It is equal to how much? CGS unit of work. It is the erg. Then comes the relation between this 1 joule and erg. Okay. Basically, 1 joule, we can also write it as, look at this here. And work done, it is equal to force multiplied with distance, right? It can be written as 1 force is Newton multiplied with meter. Okay. Multiplication in units, it is represented with hyphen. Okay. So it is Newton meter. Okay. 1 joule is equal to 1 Newton meter. This can be written as 1 Newton is equal to 10 power 5 dyne. 1 Newton is equal to how much? 10 to the power of 5 dyne. And meter is how many centimeter? 10 power 2 centimeter. When you multiply these two, you will get it as 10 power 7 dyne centimeter. Okay. So This is nothing but this dyne centimeter, you can call it as 10 power 7 erg. Is that okay? Right? So look at this. 1 joule is equal to how many erg, my dear? 10 to the power of 7 erg. Okay, please take it down. Next. So dimensional formula. Okay, how do you get the dimensional formula? It is F into S, isn't it? Dimensional formula of force is m power 1, L power 1, T power minus 2. That is the dimensional formula for force. Okay. Then what about the dimensional formula of distance or displacement? It is L to the power of 1. Okay. So when you multiply these two, obviously L power 1 into L power 1, it will become m power 1, L power 2, T to the power of minus 2. Then next slide. Okay. So what is that? Fs cos theta, scalar quantity. SI unit is joule, CGS unit is erg. 1 joule is equal to 10 power 4. Okay. Next. So generally this work done, it can be divided into 3 parts. Okay. First one is positive work. Next one is obviously negative. Few students might be understanding it directly. Okay. When it is mentioned here, it has positive. Okay. Because more than teachers sometimes is thought of the students is very fast actually. Okay. So here when you see positive, you might be knowing that another one will be negative and the third one will be 0. Okay. So now what is this positive work done? Let us discuss that. Look at this. Okay. See, if you remember, like in the previous slide, I gave that W is equal to Fs cos theta. Okay. So this work done is said to be positive when the angle between F and S is acute. Acute angle means, what is meant by acute angle? Theta should be less than 90 degree. Okay. Then in that case, it is called as acute angle. If the angle is less than 90, we call it as acute angle. Then acute angle means cos, in the acute angle, cos value will be always positive. Cos, for example, if you take cos 30, okay, it will be equal to how much? Root 3 by 2. Okay. So that it is a positive value. So in that way, work done, you will be getting it to be positive value. Is it okay? So that one we call it as positive work done when the angle between force and displacement is acute. Few people might say that if force and displacement are acting in the same direction, okay, then also you can say that work done is said to be positive. Is it okay? Or component of force. Okay. Right. Next one is, so look at this. There are a few examples here. So here, what is the angle between the force and the displacement here? It is 30 degree, which is acute. So in this case, work done by the force applied by this person, it will be positive. Okay. Then the next one is, oh, yeah, I think you're able to see that the person is actually pulling that rock at what angle? 25 degree. So the work done by that person is also positive. Okay. Next, look at this. This person is actually falling down. Okay. Gravity is pulling him down. Is it okay? So this person is also moving in the downward direction. So work done there, the angle between force and the displacement is acute. Okay. So there the work done by gravity is also positive. Okay. See, whenever you wanted to find work done, you have to check two things. In which direction force is acting? In which direction displacement is acting? Based on that, you can easily identify what is the angle between them. Then you can identify whether the work done is positive or negative. Okay. Next. Now look at this. For example, when a person is walking, friction will be acting in the forward direction. That means person will apply force in the backward direction. Okay, using his shoes or slippers, whatever it is, he will apply force on the ground in the backward direction. But the reaction of the force on the shoes will be in the forward direction. So here, when a person is walking in forward direction, friction will be acting in the forward direction only. Okay, displacement is also in the forward direction. Then the angle between these two is acute. So then work done by frictional force when a person is walking is also positive. Work done by friction is also positive. Okay, next one. Next comes negative work done. Okay, so what is meant by negative work done means, yeah, obviously, suppose, okay, if the angle between force and displacement is obtuse, okay, we have discussed that W is equal to Fs cos theta. For example, if this angle is obtuse, obtuse means theta will be greater than 90. Okay, such type of angles we call them as obtuse angles. So if the cos value is going to be obtuse, then this value will become negative. So due to that, we say that the work done by that particular force is negative. Okay, next. So here this example I'll tell you. Okay, so basically where do we observe this with negative work done is, for example, if you are projecting any body in the upward direction, gravity is acting downwards. Gravity will be always acting towards the earth. So it is acting downwards, but the body is moving in the upward direction. So both, what is the angle between this gravity and as well as that displacement? It is greater than 90. So the work done by gravitational force on a vertically projected body is negative. Okay. Similarly, walking, force applied by you. Now look at this. This person is applying force in the backward direction, but his displacement is in the forward direction. Both are opposite or they are at an obtuse angle. Then work done by force applied by your legs on the floor. Okay. When you are walking, it will be negative. Is it okay? Next. Work done by friction on a sliding body. For example, you take a sliding body is sliding on this. Okay, displacement is this way. Friction is acting opposite. Friction will always tries to friction. It is trying to oppose the sliding of this body. Okay, so here what is the angle between displacement and that friction is? It is greater than 90. That is almost 180 there. So their work done by that particular frictional force is also negative. Okay, next. Let's go for the next. Okay, next one is zero work done. Okay, zero work done. What is meant by zero work done? Means if the force and displacement on a body are perpendicular to each other. Again, work done is equal to what is the formula? Fs cos theta. For example, if theta is becoming 90 degrees, that means if the force and displacement are perpendicular to each other. Okay, then cos 90 is how much? 0. So work done by that particular force and displacement is taken to be force on the displacement, it is taken to be 0. Okay, so in this basically there are two cases. It is not about only perpendicular. For example, if the displacement of the body is 0 or if theta is equal to 90 degrees, in both cases work done can be 0. In the both cases, work done will be 0. Okay. Like for example, you are applying force on a wall, but the wall doesn't displace, right? Okay. Suppose in your room, if you are applying force on the wall and if you are able to displace that wall, that is different case. Okay. Let us talk about some reality here. Okay. You apply some force on the wall, and if that wall is not moving anywhere, it is there only, right? There the displacement is 0. Okay, unless you are a Superman. Okay. Then in that case, work done will be 0. And for example, if force and displacement are perpendicular to each other, then in that case also work done will be 0. For example, let us consider a person called Ramesh. Okay, Ramesh is our imaginary character in our classes, my dear. So sometimes as an example, I'll use his name. If you, any one of you who is seeing this video, if your name is Ramesh, I'm really sorry for that. If you are feeling bad about it, okay? But no, Ramesh, I'll be using it every time for him to give the example in physics. Okay, you are a role model there. Okay, yeah. So this person is walking forward. Okay, but his weight is actually acting vertically downwards. What is the work done by gravity here? Both are perpendicular to each other. No, force and the displacement of the person both are perpendicular to each other. In that case, we will take that work done by the gravitational force is 0. Is it okay? We have to tell every time it has work done by which force. Work done by which force, we have to be careful there. Okay. So here I am talking about gravitational force. Suppose when you are standing here, there is another force in the upward direction, that is a normal reaction. Even normal reaction is also perpendicular to displacement. So work done by normal reaction is also 0. Okay. Work done by gravity when you are walking, it is 0. Then it will be equal to 0. Next one is work done by centripetal force on a body in circular motion. For example, a body is moving in circular path. Okay. This is the center, let us take, and here there is a body. Okay. It is making circular path. Okay. Its velocity actually it will be tangential. Centripetal force will be acting towards the center. What is the angle between them? It will be equal to 90 degree. Okay. So work done by this centripetal force on this moving body, it will be equal to 0. Okay. So those are the cases regarding 0 work done by dear. Please take it down. So now we'll do the questions based on this. Okay. This is only the video of part 1 in the work. Remaining, there are few more concepts that we'll be discussing it in the next class after these questions. Okay. Look at this. Now, so here if you observe, force is given as F vector is equal to 2I cap plus 7J cap minus K cap. S vector is equal to minus I cap plus 3J cap minus 2K cap. Then what is the work done here? Okay. So here it is given in vector form, right? We are having different formulas for work done. Okay. That is work done is equal to F vector dot S vector, or it is also equal to Fs cos theta, right? So out of these two, which one should we apply? Obviously F vector dot S vector, because here it is given in here it is given in vector form. For example, if they gave angle, then you can go for this. Okay. So now let us do this. So it is 2I cap plus 7J cap minus K cap dot minus I cap plus 3J cap minus 2K cap. Okay. So when you do the dot product, what we have to do? Simply we have to multiply the coordinates of I cap, multiply the coordinates of J cap, multiply the coordinates of K cap, and add all this. Okay. So here it will be 2 here. Okay. This minus 1 here. Okay. Plus similarly 7 here. What is the J cap here? 3. Okay. So this is 7 into 3 plus here how much is there? Minus 1 for K cap, and this side K cap it is how much? Minus 2. Okay. So dot product means we should multiply the coordinates of I cap, J cap, K cap, and add all. Okay. So here what will be your answer, my dear? Minus 2 plus 7 3s are 21 plus 2. Okay. So minus 2 plus 2 can be cancelled. So this will be 21 Joule is your answer, my dear. Okay. That is how we do the work done. Okay. Next one. I'm going to the next question. Okay. Yeah. That is a force F is applied on a lawn mover at an angle of how much it is? 60 degree with the horizontal. Okay. If it moves through a distance y, then the work done by the force is how much? Okay. So look at this. There is a lawn roller. Lawn roller means there will be in cricket matches and all you might have seen, no? Okay. Right. There will be a roller, and here there will be some handle here. Let us suppose that force is F. And this lawn roller is moving by how much angle? 60 degree. I mean, it is force is applied at an angle 60 degree. Basically, this lawn rollers, no, they'll be moving on the horizontal floor or maybe on the inclined floor also. But anyway, here force is acting at an angle 60 degree there with the horizontal. So if it is moving through a distance of y along that horizontal, okay, then what is the work done? Okay. So here in this case, angle is given. Then we will use the formula if W is equal to Fs cos theta. So what is that F value here? F. S is how much here? S is the displacement. How much it is? Y. What is the angle between force and displacement in this case, my dear? 60 degree. Cos 60. So anyway, angle is acute. So work done will be positive only here. So it is F into Y into cos 60 is 1 by 2. So what is that? F into Y divided by 2. Is it okay? So this is the work done by the course. Okay. So just small basic points only we have discussed in this particular video. I don't want to make a long video on this total work. Okay. Learning should take place, in a process, like in the sense, everything it should not be at a time. Okay. Slowly, part by part, if you learn, no, it will be more understandable for you in the concept, because we can repeat that formulas many times there. Okay. So yeah, second part will be coming within the very few days. Okay, maybe tomorrow or day after tomorrow I'll be posting it. So let us do the remaining part of work done there. There will be more applications in that part 2 video. You'll be having a lot of application based concepts on that work done. Okay, so those we'll be doing. So that video also is also going to be very good. Okay, so that's the class and that's the video. Okay, thank you all of you. So if you really like this particular video, you please like, share and subscribe this channel. Okay, and physics AAR. Okay, channel name. Okay, thank you all of you. Bye.